February 9, 1945, off Fedje Island, Norway. Lieutenant Commander James Launders, 25, from Liverpool, pressed his ear against the hydrophone headset in HMS Venturer's control room. Through the static came a sound that made his pulse quicken, the rhythmic beat of diesel engines somewhere in the dark water ahead. His fingers tightened on the chart table edge. The North Sea winter had turned the water into liquid ice, and somewhere in that frozen darkness prowled a German submarine, both vessels submerged, both hunting, both blind except for sound. Could they find the enemy before the enemy found them? Launders had tracked U-boats for 18 months, but never like this. Surface attacks gave you the advantage of sight. Periscope depth let you see your target, calculate distance, measure speed. Down here at 60 meters, sight meant nothing. The hydrophone operator, Petty Officer Arthur Knowles, adjusted his equipment and listened harder. The German engines grew louder, closer. What Launders didn't know, within 3 hours, he would make history. The action he was about to take would create the only confirmed instance of one fully submerged submarine destroying another fully submerged submarine using torpedoes alone. No Navy had achieved this before. None would achieve it again. The problem started 72 hours earlier when British intelligence intercepted German naval communications. U-864 had departed Bergen carrying something unusual. Not troops, not standard munitions. The cargo manifest made London's Naval Command issue immediate orders: stop that submarine at any cost. HMS Venturer received the alert on February 6th. German submarine U-864 heading north. Mission: transport advanced technology to Japan. The intelligence report detailed the cargo: 67 tons of mercury sealed in steel flasks, 2 disassembled Me-262 jet engines, and technical drawings for jet aircraft production. If that cargo reached Japan, the Pacific War would shift dramatically. Launders brought his crew to action stations and positioned Venturer along U-864's projected route. The weather deteriorated rapidly. Storm winds pushed waves to 30 feet. Surface patrol became impossible. He made the decision to hunt underwater. The German commander didn't suspect pursuit. Oberleutnant Ralph Reimar Wolfram, 28, from Hamburg, had survived 3 Atlantic patrols and considered the Norwegian coast relatively safe. British destroyers dominated the surface, but submarines rarely hunted other submarines while submerged. The tactic was considered impractical. Too many variables, too little information, nearly impossible calculations required. Wolfram's confidence came from experience. He'd evaded depth charge attacks off Newfoundland, survived convoy battles in the western approaches, and delivered supplies to isolated German garrisons along the Norwegian coast. This mission seemed straightforward by comparison. Run north underwater, surface briefly for navigation fixes, reach the Arctic Ocean, then head east toward Japan through waters the British couldn't effectively patrol. His crew of 73 men settled into the routine of underwater transit. The boat's diesel engines drove them forward at 6 knots, slow enough to conserve fuel, but fast enough to maintain schedule. Every 6 hours, Wolfram checked their position and adjusted course. The Mercury cargo sat secured in the aft torpedo room, each flask marked with warnings about toxic contamination. The British Admiralty understood what that mercury meant. Jet engines required precise manufacturing tolerances. Traditional lubricants failed at high temperatures. Mercury-based compounds solved the problem, but Germany's domestic mercury supply had been exhausted by February 1945. The cargo aboard U-864 represented Japan's only realistic path to mass-producing jet fighters before Allied bombers reduced their cities to ash. Admiral Max Horton issued the order personally: sink U-864 before she clears Norwegian waters. He assigned the task to Venturer because Launders had demonstrated unusual skill in underwater maneuvering during training exercises. The young commander had practiced a theoretical tactic, calculating target position using only hydrophone data, then firing torpedoes in a spread pattern to compensate for uncertainty. The tactic had never been tested in combat. Naval doctrine considered it theoretical at best, suicidal at worst. Fire torpedoes blind and you reveal your position. Miss the target and the enemy counterattacks. Hit your own torpedo with another torpedo and both explode prematurely. The variables multiplied into chaos. But Launders studied the math. If you could determine target bearing through hydrophone triangulation, estimate range through sound intensity, calculate depth through propeller harmonics, and predict course through rate of bearing change, then theoretically you could plot an intercept solution. Theoretically. How many men would die testing that theory? British submarines carried 8 torpedoes in their forward tubes. Each Mark VIII torpedo cost $3,500, weighed 1,750 pounds, and ran at 45 knots for 5,000 yards. Fire all 8, and you'd emptied your arsenal, return to base without a kill, and face questions about wasted resources. The pressure on Launders came from every direction. Stop the German cargo, validate the tactic, justify the risk, bring your crew home alive. February 9th brought the convergence. Venturer patrolled a 10-square-mile zone near Fedje Island. Knowles detected the contact at 0947 hours, distant at first, barely distinguishable from ocean noise, then stronger. The sound pattern matched German diesel engines, a Type 9 U-boat running submerged. Launders ordered the crew to silent routine. Every unnecessary machine shut down. Men moved carefully to avoid metallic sounds. The submarine drifted forward on minimal power while Knowles tracked the target. The bearing changed slowly. The German was zigzagging, a standard evasion pattern to avoid detection. The numbers seemed impossible. 2 submarines hunting underwater, neither able to see the other, both maneuvering in 3 dimensions, all calculations based on sound alone. But Knowles confirmed every detail through repeated bearing checks. The target was real, moving, and getting closer. Launders pulled out his plotting board and began the calculations that would determine whether 73 German sailors or 42 British sailors died in the next hour. Bearing, 347 degrees. Range, estimated 3,800 yards based on sound intensity. Depth, 60 meters based on propeller cavitation frequency. Course, northward with 20-degree zigzags every 8 minutes. The tactical problem crystallized into simple geometry. U-864 was zigging toward them. In 4 minutes, she would zag away. The firing solution required predicting where the target would be when 4 torpedoes reached that position, accounting for the target's evasive maneuvers, depth changes, and speed variations. Lieutenant Peter Scaife, 24, from Cornwall, manned the torpedo data computer. The mechanical calculator whirred as Scaife input bearing changes. The solution came back in angles and ranges. Fire 4 torpedoes in a spread pattern, each aimed at a different predicted position, creating a 200-yard kill zone the German couldn't evade even if he detected the attack and took emergency action. The plan depended on one assumption. Wolfram would maintain his zigzag pattern. If he changed tactics, all 4 torpedoes would miss. If he went deep suddenly, they'd pass overhead. If he went shallow, they'd pass underneath. If he accelerated, they'd arrive late. If he stopped, they'd overshoot. Would the calculations hold? The technology that made Launders' attack possible came from an unexpected source: peacetime whale hunters. Before the war, commercial vessels used underwater listening devices to track whale pods through Arctic waters. The British Admiralty adapted that technology into ASDIC, an acoustic detection system that transformed submarine warfare. But ASDIC had limitations. The active sonar version sent sound pulses that revealed your position. The passive hydrophone version gave you silence and stealth, but reduced information. You heard the enemy. You couldn't see him. Launders had trained extensively with passive hydrophones at the submarine school in Rothesay. Instructors emphasized the physics. Sound traveled through water at 4,900 feet per second, faster than through air but slower than light. Temperature layers bent sound waves. Salt content affected transmission. Submarine hulls created acoustic shadows. Propellers generated specific frequency signatures. Could anyone master those variables well enough to hit a maneuvering target? Lieutenant Commander Launders had demonstrated the skill during exercises off Scotland. In December 1944, he tracked a friendly submarine for 6 hours using only hydrophone data, predicted its course changes, and positioned Venturer for simulated attacks that would have resulted in kills. The exercise commander noted, "Launders shows exceptional ability in acoustic tracking. Recommend assignment to advanced patrol duties." That recommendation brought him to Norwegian waters, hunting U-864. The hydrophone system aboard Venturer consisted of 4 arrays mounted along the hull. Each array contained multiple sensors that detected sound pressure from different directions. Knowles wore headphones connected to an amplifier that boosted weak signals and filtered out background noise. A dial indicator showed relative bearing, the direction from which sound originated. What happened next would determine whether acoustic tracking could work in real combat. Knowles reported bearing changes every 30 seconds. Launders plotted each reading on his chart. The pattern emerged. U-864 maintained 6-knot speed, zigzagged through 40-degree arcs, spent 8 minutes on each leg. The predictability gave Launders his advantage. Wolfram was following standard procedure, which made him calculable. The torpedo data computer processed the information through mechanical gears and cams. Input: target bearing, estimated range, estimated speed, estimated depth. Output: firing angles for each torpedo, time delays between shots, spread pattern dimensions. Scaife cranked the handle and read the results. Solution ready. 4 fish in a diamond pattern, 200-yard spread. Recommend tubes 1 through 4. Launders studied the solution. The torpedoes would run for 90 seconds before reaching the target zone. During that time, U-864 would travel 300 yards. The spread pattern accounted for uncertainty. 1 torpedo aimed at the predicted position, 3 others aimed at alternate positions 100 yards apart. The geometry created a kill zone, measuring 200 by 200 yards. If Wolfram zigged left, torpedo 1 would miss, but torpedo 2 would hit. If he zagged right, torpedo 3 would connect. If he went deep, torpedo 4 running 10 feet lower would intercept. If he maintained course, torpedo 1 would strike amidships. The mechanism worked through simple physics. Each Mark VIII torpedo carried a 750-pound Torpex warhead, a high-explosive mixture of RDX, TNT, and aluminum powder. Detonation created a shock wave that traveled through water faster than through air. The pressure wave would rupture the U-boat's pressure hull, flood internal compartments, and send the submarine to the bottom before crew members could react. Advantages became clear through comparison. Surface attacks required periscope depth, which exposed the attacking submarine to counterfire. Aircraft attacks required good weather and daylight. Destroyer depth charge attacks required multiple passes and often failed. Submerged torpedo attacks offered stealth and surprise. The target wouldn't know death was approaching until torpedoes were already running. Before acoustic tracking, submarine commanders relied on sight-based attacks. Surface the boat, use the periscope, measure range with optical equipment, fire torpedoes, submerge immediately. The tactic worked against merchant ships and surfaced U-boats. It failed against submerged submarines because you couldn't see them. After acoustic tracking development, the equation changed. Sound penetrated darkness. Hydrophones detected submerged targets at ranges exceeding 5,000 yards under ideal conditions. Patient operators could track targets for hours, building a precise picture of enemy movements without ever surfacing or revealing their position. The enemy would document the shift years later. German naval archives recovered after the war contained a report from February 1945. British submarines demonstrate new capability. Multiple instances of accurate torpedo fire against submerged U-boats suggest acoustic tracking technology has advanced beyond our countermeasures. Recommend immediate development of silent running procedures. The problem? Germany couldn't solve what they didn't fully understand. Opposition to acoustic attack tactics came from unexpected quarters. Senior Royal Navy officers considered the method too risky. Captain George Phillips, submarine squadron commander, wrote in January 1945, "Firing torpedoes, blind invites disaster. The attacking submarine reveals its position, wastes ammunition, and achieves no measurable advantage over patient tracking, followed by surface attack." But younger commanders like Launders disagreed. They'd seen U-boats escape surface attacks by crash diving. They'd watched targets slip away during the time required to reach periscope depth. They'd calculated that acoustic attacks offered better odds despite the risks. The debate intensified after several failed attempts. In December 1944, HMS Seraph fired 4 torpedoes at a submerged contact off Norway. All missed. The target, later identified as U-864, counterattacked with acoustic torpedoes and forced Seraph to withdraw. The incident seemed to prove the critics right. Acoustic attacks wasted resources and endangered British crews. Admiral Horton defended the tactic. "We're developing new capabilities. Failure during development is expected. The question is whether the concept has merit, not whether initial attempts succeed perfectly." He authorized continued training and assigned Venturer to Norwegian patrol with explicit permission to attempt acoustic attacks against opportunity targets. The authorization came with one restriction: do not engage unless confident of success. Do not waste torpedoes on low-probability shots. Do not risk your boat unnecessarily. Launders accepted those terms. He would wait for the perfect opportunity. Lieutenant Scaife questioned the mathematics. "Sir, we're calculating in 3 dimensions with partial information. Error margins could exceed 200 yards. The spread pattern compensates, but what if the target's deeper than estimated? What if he's faster? What if our range calculation is wrong by 500 yards? Valid concerns. Launders addressed each one. Depth estimation relied on propeller harmonics. Deeper targets generated lower frequencies. Speed estimation used bearing rate. Faster targets changed, bearing more quickly. Range estimation combined intensity measurements with bearing changes. Closer targets produced stronger signals and faster bearing shifts. "We're not guaranteeing a hit," Launders explained. "We're creating probability. 4 torpedoes with a 200-yard spread give us roughly 60% chance of at least 1 hit. Surface attacks under these conditions would give us maybe 20% chance. We're tripling our odds." The math convinced Scaife. He recalculated using different assumptions and reached similar conclusions. The acoustic attack method wasn't certain, but it was significantly better than alternatives given the tactical situation. Knowles reported steady bearing changes through 10-30 hours. U-864 maintained its pattern. Launders ordered the crew to action stations. 4 torpedoes loaded, tubes flooded, outer doors opened quietly. The attack phase began. The path to that moment started months earlier during exercises in the Firth of Clyde. Launders took command of HMS Venturer in November 1944 and immediately began training his crew in acoustic tracking procedures that existed only in theoretical manuals. The first test came on November 18th against HMS Sturdy, a friendly submarine playing the role of enemy target. Launders positioned Venturer at 50 meters depth and ordered Knowles to track Sturdy's movements using hydrophones alone. No periscope, no visual confirmation, pure acoustic hunting. Knowles detected the target at 4,200 yards. The bearing drifted slowly right. Sturdy was crossing ahead. Launders plotted the movement and calculated an intercept course. Venturer turned to parallel the target's estimated track. For 40 minutes they maintained contact through sound alone. Then Sturdy executed an emergency turn. The bearing swung rapidly as the target maneuvered. Knowles struggled to maintain contact through the confusion of propeller noise and hull turbulence. The signal faded, strengthened, faded again. Launders adjusted course based on his last solid bearing, and after 3 anxious minutes, Knowles reacquired the target. Would they lose contact during real combat? The exercise continued for 3 hours. Sturdy maneuvered aggressively, changing depth, speed, and course every few minutes. Launders maintained contact through each evolution, demonstrating that persistent tracking was possible even against an alert opponent. The exercise commander scored the evolution as successful but noted, tracking capability confirmed. Attack capability remains unproven. That challenge defined the second test. On December 2nd, Launders received permission to conduct a simulated attack using practice torpedoes against HMS Statesman. The scenario replicated combat conditions, both submarines submerged, no communication, Statesman maneuvering evasively while Venturer hunted. The problem multiplied immediately. Practice torpedoes ran true but carried no warheads. Scoring required visual confirmation that the torpedo passed within lethal range of the target. Statesman would observe whether torpedoes came close enough to achieve a kill. The pressure mounted, missed badly, and the entire concept would face rejection. Launders tracked Statesman for 90 minutes, building a precise picture of the target's movement pattern. The other submarine zigzagged through 30-degree arcs, changed depth every 12 minutes, and varied speed between 4 and 7 knots. Complex maneuvers designed to defeat acoustic tracking, but patterns emerged. Statesman's commander favored certain depths. His zigzag timing became predictable after 5 cycles. His speed changes correlated with depth changes. Launders recognized the rhythm and calculated a firing solution. At 14:47 hours, Venturer fired 4 practice torpedoes in a spread pattern. The weapons ran hot and true, their propellers generating the distinctive whine of Mark VIII, fish moving at 45 knots. Aboard Statesman, lookouts tracked the incoming weapons and reported their positions. 2 torpedoes passed within 50 yards, lethal range. 1 passed at 80 yards, marginal. 1 missed by 200 yards. The exercise commander scored it as 2 kills. Venturer demonstrates that acoustic attack is viable under ideal conditions. Recommend additional training with emphasis on firing solution accuracy. Adjustments followed. Launders worked with SCAFE to refine the torpedo data computer inputs. They discovered that small errors in range estimation created large errors in firing solutions. A 10% range error translated to 40-yard position errors at impact. The spread pattern needed to compensate for that uncertainty. They modified the diamond pattern to a box pattern, 4 torpedoes arranged in a rectangle rather than a diamond. The box measured 200 yards long by 150 yards wide, oriented perpendicular to the target's estimated course. Any target inside that box would receive at least 1 hit, probably 2. The third test occurred on December 15th against HMS Sanguine. Weather conditions deteriorated. Storm waves created noise that interfered with hydrophone reception. Launders struggled to maintain contact as wind-driven turbulence generated false signals. Knowles reported 6 separate contacts, 5 of which proved to be noise artifacts. Could they distinguish real targets from false contacts during storms? The answer came through patience. Knowles learned to identify true submarine contacts through propeller signature analysis. Diesel engines generated rhythmic pulses. Electric motors produced high-frequency whines. Natural sounds, storms, sea life, thermal layers lacked that mechanical regularity. After 2 hours, Knowles confidently identified Sanguine and maintained solid contact despite heavy weather. Launders fired the attack at 16 and 23 hours. 3 torpedoes passed within 60 yards of Sanguine, all scored as kills. The 4th torpedo malfunctioned and ran deep, missing by 150 yards. Still, 3 hits from 4 shots exceeded expectations under difficult conditions. The 4th test came on January 8, 1945, against HMS Spiteful in Norwegian waters near Bergen. The scenario simulated a U-boat transit. Spiteful would move from point A to point B, while Venturer attempted intercept. The distance, 40 nautical miles through waters known for difficult acoustic conditions. Launders positioned Venturer along the projected track and waited. Knowles detected Spiteful at extreme range, 7,800 yards, barely audible. They tracked the contact as it approached, refined their position estimates, and moved to an intercept position. At 6,200 yards, Launders ordered the attack. The firing solution required prediction. Spiteful was moving, Venturer was moving. Torpedoes would take 110 seconds to reach the target zone, and during that time, both submarines would travel significant distances. Scaife calculated intersection geometry using vector addition, target velocity plus torpedo velocity minus own velocity equals relative motion. 4 torpedoes launched at intervals of 8 seconds. The spread pattern created sequential arrival times. The target couldn't evade all 4 because the later torpedoes would catch him during evasive maneuvers. At least that was the theory. Results exceeded expectations. All 4 torpedoes passed within 70 yards of Spiteful. The submarine's commander reported, "Never saw them coming, no warning. Would have been killed instantly. Recommend immediate tactical revision to account for this threat." That report reached the German naval staff through unknown channels. In late January, U-boat headquarters issued new guidance. British submarines demonstrate submerged attack capability, recommend irregular zigzag patterns, frequent depth changes, silent running when transiting known British patrol areas. The 5th test never happened. On February 6th, British intelligence intercepted German communications about U-864's departure. The Admiralty canceled training exercises and ordered Venturer to Norwegian waters. Real combat would validate or disprove everything they'd practiced. Launders briefed his crew on the mission. "We're hunting a specific U-boat carrying critical cargo. Intelligence indicates the target will transit our patrol zone within 72 hours. Our orders are to sink her before she reaches open ocean. This is not an exercise. The target will not surface for scoring. We fire real torpedoes with real warheads. People will die, Germans if we succeed, possibly us if we fail." The crew understood. They'd trained for this moment through 5 months of exercises. The techniques were proven. The equipment was reliable. The tactics were sound. Now came the test that mattered. HMS Venturer departed Lerwick on February 6th and reached station off Fiji Island on February 8th. Launders positioned the submarine along the most likely German route, the channel between the Norwegian coast and the offshore islands. Water depth, 180 meters. Bottom composition, rock and gravel. Good acoustic reflection. Current, 1.5 knots northward. Temperature, 4 degrees Celsius. Conditions favored acoustic tracking. They waited. February 8th passed without contact. Launders remained submerged to avoid detection by German coastal radar. The crew rotated through watch stations, maintaining constant hydrophone monitoring. Knowles listened through each watch, familiarizing himself with the local acoustic environment, fishing boat engines, whale sounds, current noises, thermal layer reflections. How long could they wait without compromising the mission? February 9th brought the answer. At 09:47 hours, Knowles detected diesel engines bearing 347 degrees. The signature matched intelligence descriptions of Type 9 U-boat propulsion. Range, estimated 4,000 yards based on signal strength. Depth, estimated 60 meters based on propeller harmonics. Course, generally northward, with irregular maneuvers. Launders ordered action stations. The wait was over. Real combat began. Knowles tracked the target through steady, bearing changes. U-864 zigzagged through its evasion pattern, unaware that HMS Venturer had detected every movement. Launders plotted each course change and recognized the rhythm: 8 minutes per leg, 40-degree turns, constant depth at 60 meters. The German commander was following doctrine precisely, which made him predictable. At 10:20 hours, Launders made his decision. The geometry was favorable. Range had closed to 3,000 yards. The target's next zig would bring him closer. In 4 minutes, he would zag away. The firing window would open for approximately 90 seconds during the transition between zig and zag. Could they execute the attack before that window closed? Scaife input final calculations into the torpedo data computer. Target bearing, 351 degrees. Estimated range, 2,800 yards. Estimated speed, 6 knots. Estimated depth, 60 meters. Own speed, 3 knots. Own depth, 55 meters. Solution: fire 4 torpedoes in box pattern, each separated by 8 seconds, spread covering 200 by 150 yards. Launders verified the mathematics personally. Each torpedo would run for 85 seconds before entering the kill zone. During that time, U-864 would travel 290 yards. The lead torpedo aimed at the predicted position. The second torpedo aimed 75 yards right of track to catch a starboard turn. The third torpedo aimed 75 yards left to catch a port turn. The fourth torpedo ran 10 meters deeper to catch an emergency dive. "Stand by tubes 1 through 4, Launders ordered. "Outer doors open." Hydraulic systems opened the torpedo tube doors slowly to minimize noise. The evolution took 15 seconds. Green lights illuminated on the firing panel. Tubes ready. Launders watched the clock and the bearing indicator simultaneously. U-864 was completing its zig turn. In 30 seconds, the target would steady on the new course. That was the moment. Fire 1. The torpedo ejected from its tube with compressed air. The Mark VIII weapon surged forward, its propeller spinning up to full speed. The distinctive whine propagated through the water in all directions. Aboard U-864, if anyone was listening carefully, they might hear that sound and realize death was approaching. Fire 2. 8 seconds later. Fire 3. 8 seconds after that. Fire 4. The final torpedo. All weapons running hot and true. Launders ordered immediate evasive maneuvers. Venturer turned hard left and dove toward 80 meters. The tactical situation reversed. Now they were the hunted. If U-864's crew heard the attack and responded quickly, German acoustic torpedoes might already be searching for Venturer's position. Silence fell in the control room. 85 seconds felt like 85 minutes. Knowles kept his headphones on, listening for any change in U-864's engine noise, acceleration, deceleration, depth change, anything that might indicate detection and evasion. The seconds ticked past, 60 seconds, 70, 80. Then an explosion shook the ocean. The shock wave hit Venturer's hull with a metallic clang that resonated through every compartment. Crew members grabbed handholds to steady themselves. Knowles yanked his headphones off. The explosion volume would have damaged his hearing. "One hit," Scaife reported. "Solid hit. Breaking up noises bearing 352 degrees. Would anyone survive?" Knowles put his headphones back on carefully and listened. The diesel engines had stopped. New sounds replaced them: metallic grinding, bulkhead collapsing, air escaping, debris falling. The acoustic signature of a submarine dying. U-864 was going down. The torpedo had struck the German submarine amidships, penetrating the pressure hull between the control room and the engine room. The 750-pound Torpex warhead detonated inside the pressure hull, creating a blast wave that ripped through internal compartments. The explosion ruptured fuel tanks, ignited diesel vapors, and blew the submarine into 2 sections. 73 men died instantly. The pressure hull failure at 60 meters depth meant the ocean pressure, 87 pounds per square inch, flooded internal spaces in seconds. Crew members in the aft section were killed by the initial explosion. Those in the forward section drowned before they could reach emergency breathing equipment. Oberleutnant Wolfram likely never knew what killed him. The torpedo approached from his starboard quarter, an angle his hydrophone operator couldn't effectively monitor due to interference from the submarine's own machinery. The weapon ran quietly until the final 10 seconds when its propeller cavitation became audible. By then, evasion was impossible. The Mercury cargo went down with the submarine. 67 tons of toxic metal in steel flasks scattered across the ocean floor at 180 meters depth. The ME-262 jet engines, packed in waterproof crates, settled into the mud beside the wreckage. Technical drawings sealed in watertight containers drifted with the current before sinking. Japan's hope for jet fighter production died in 85 seconds of torpedo run time. Launders ordered Venturer to return to periscope depth cautiously. The risk remained. Other U-boats might be operating nearby, drawn by the explosion. He waited 20 minutes at 80 meters, listening for contacts. Nothing. The ocean was silent except for the fading sounds of U-864's wreckage settling on the bottom. At 11:42 hours, Venturer reached periscope depth. Launders raised the periscope and scanned the surface. Oil slick spreading from the impact point, debris field, wood fragments, fabric, metal pieces. No survivors, no lifeboats, no one in the water. The attack had achieved complete destruction. He lowered the periscope and ordered course set for base. HMS Venturer withdrew from the area at 8 knots, running submerged until clear of Norwegian coastal waters. The return trip took 14 hours. Launders drafted his after-action report during the transit, documenting every detail of the engagement. The report reached Admiralty on February 11th. Naval intelligence confirmed U-864's destruction through multiple sources: German radio traffic discussing the submarine's failure to report, Norwegian resistance operatives observing the oil slick, and acoustic analysis of explosion recordings. The kill was official, but the significance took longer to emerge. February and March brought dozens of submarine actions throughout Atlantic and Pacific theaters. U-864's loss seemed routine. One more U-boat sunk among hundreds destroyed during the war. The Admiralty filed Launders' report without special recognition. Then analysts began detailed review. Someone noticed the engagement specifics. Both submarines submerged, no visual contact, torpedo attack based purely on acoustic tracking. The tactical innovation became apparent. Venturer had achieved something unprecedented. A second analysis team examined the acoustic data. The bearing plots, range estimates, and firing solution calculations demonstrated sophisticated methodology. Launders had solved a problem that naval theorists considered nearly impossible: hitting a maneuvering underwater target using sound alone for targeting. The Royal Navy's Submarine Command reviewed the engagement in March 1945. Captain George Phillips, who had opposed acoustic attack tactics, revised his assessment. Launders has proven the concept viable. Recommend immediate dissemination of techniques to all submarine commanders. The tactical advantage justifies the ammunition expenditure and position disclosure. Risks. Training programs expanded rapidly. Submarine crews throughout the fleet received instruction in acoustic tracking procedures. The hydrophone operators attended specialized schools where they practiced contact identification, bearing tracking, and range estimation. Torpedo data computer operators learned the modified firing solutions that enabled submerged attacks. Did other navies learn from Venturer's success? German naval intelligence captured partial information about the engagement through signals intercept. A message dated March 15, 1945, from U-boat headquarters to all operational submarines warned: British demonstrate capability for submerged torpedo attacks. Exercise extreme caution during transit through British patrol areas. Implement irregular maneuvering patterns. Minimize time at periscope depth. Maintain acoustic watch during all submerged operations. But the warning came too late for operational implementation. Germany's submarine force was collapsing by March 1945. Allied air superiority made surface transit suicidal, fuel shortages, limited patrol endurance, crew quality declined as experienced sailors died, and inadequately trained replacements filled their positions. The few U-boats still operating couldn't effectively respond to the new British tactics. The Soviet Navy obtained detailed information about Venturer's attack through their liaison officers at British Naval Headquarters. Soviet submarine commanders studied the technique and adapted it to their own operations in the Baltic and Black Seas. Post-war Soviet submarine doctrine incorporated acoustic attack procedures directly derived from Launders's methods. The United States Navy received complete tactical briefings in April 1945. American submarine commanders operating in the Pacific showed intense interest. Japanese submarines remained a threat, and acoustic attack techniques offered a new tool for dealing with them. The USS Batfish had sunk 3 Japanese submarines in surface attacks during February 1945, but submerged attack capability would have simplified those engagements significantly. HMS Venturer returned to patrol duties in March 1945. Launders conducted 2 additional patrols off Norway before the German surrender in May. His crew sank no additional submarines but maintained constant acoustic surveillance of Norwegian waters, deterring U-boat operations through their presence alone. The war ended before acoustic attack techniques saw widespread combat use. Venturer's engagement with U-864 remained the only confirmed instance of a submerged submarine sinking another submerged submarine with torpedoes. The tactical innovation proved viable, but arrived too late for extensive combat application. How would history remember this achievement? During the 3-hour engagement from detection to confirmed kill, HMS Venturer fired 4 torpedoes at a target she never saw, achieving 1 catastrophic hit that destroyed U-864 and killed all 73 crew members. This represented the only successful submerged submarine-versus-submarine torpedo attack in naval history. No other submarine force, British, American, German, Soviet, or Japanese, achieved this feat during World War II. The numbers demonstrated unprecedented precision in blind firing. Launders calculated his target's position using bearing data that changed 40 degrees over 90 minutes of tracking. His firing solution predicted the target's location 85 seconds into the future, accounting for 3-dimensional movement at 6 knots through a 200-yard error margin. 1 torpedo out of 4 struck home, a 25% hit rate against a maneuvering target using acoustic tracking alone. What made one submarine crew achieve what dozens of others couldn't? The strategic impact flowed through multiple channels. Most immediately, Japan lost critical jet engine technology that might have restored air superiority over the home islands. The 67 tons of mercury aboard U-864 represented 6 months of Japanese domestic production, enough to manufacture lubricants for 300 jet engines. The Me-262 blueprints and components would have accelerated Japanese jet development by 12 to 18 months, potentially fielding operational squadrons before B-29 bombing campaigns destroyed Japan's industrial capacity. That tactical success prevented a broader strategic shift. If Japanese engineers had received German jet technology in spring 1945, the war's conclusion might have extended into 1946. American casualties during Operation Downfall, the planned invasion of Japan, would have increased substantially against opposition, including jet fighters. The atomic bombs dropped on Hiroshima and Nagasaki might not have been sufficient to force surrender if Japan possessed technological superiority in key domains. The operational impact affected U-boat operations throughout the final months of war. After U-864's loss, German Submarine Command issued restrictions on underwater transit through British patrol zones. Submarines received orders to surface only when absolutely necessary, maintain irregular maneuvering patterns, and assume constant hostile acoustic surveillance. These restrictions reduced operational effectiveness. Submarines moved more slowly, consumed more fuel on evasive routing, and completed fewer patrols. The doctrinal impact reshaped submarine warfare theory. Before Venturer's attack, naval doctrine considered submerged engagements impractical due to targeting difficulties. After the engagement, every major navy revised its tactical manuals to include acoustic attack procedures. Post-war submarine training emphasized hydrophone operations, bearing tracking, and blind firing calculations. Legacy evolution continued through the Cold War decades. Nuclear submarines inherited acoustic tracking capabilities far superior to World War II hydrophones. Modern sonar systems could detect targets at ranges exceeding 50 miles under favorable conditions. Digital fire control computers calculated three-dimensional intercept solutions in seconds rather than minutes. Acoustic homing torpedoes eliminated the need for precise firing solutions. Modern weapons adjusted their course during the attack run. But the fundamental innovation remained Launders' achievement. He proved that submarines could hunt and kill other submarines while both remained submerged. That capability became central to Cold War submarine doctrine. Soviet and American attack submarines spent decades hunting each other through the world's oceans, employing direct descendants of the techniques Venturer demonstrated in 1945. The technical principles influenced civilian applications as well. Commercial shipping adopted acoustic tracking for collision avoidance. Oceanographic research vessels used hydrophone arrays for marine life tracking. Oil exploration companies employed acoustic sensors for subsurface mapping. The mathematics of bearing tracking and position estimation found uses far beyond military applications. Lieutenant Commander James Launders received the Distinguished Service Order for the U-864 engagement. The citation read, "For exceptional skill and determination in the successful prosecution of an attack against an enemy submarine while both vessels were submerged." Lieutenant Commander Launders demonstrated tactical innovation and precise calculation under difficult conditions, achieving a kill that validated new methodologies in submarine warfare. Launders continued submarine command through 1946, then transitioned to staff positions within the submarine service. He retired from the Royal Navy in 1963 as a Rear Admiral, having influenced submarine doctrine development through 2 decades of peacetime evolution. He died in 1986 at age 66, having witnessed nuclear submarines employ tactics he pioneered in diesel boats during the war. Petty Officer Arthur Knowles, the hydrophone operator whose precise bearing reports enabled the attack, received a mention in dispatches. He remained in submarine service until 1955, training subsequent generations of sonar operators in acoustic tracking techniques. His instructional materials became standard references throughout NATO submarine forces. Could this engagement have been prevented? Lieutenant Peter Scaife, who calculated the firing solution, transferred to submarine design work after the war. He contributed to the development of improved fire control computers that automated the calculations he performed manually aboard Venturer. His work influenced British submarine designs through the 1960s. Oberleutnant Ralph Reimer Wolfram and the 72 other crew members of U-864 received posthumous recognition from the German government decades later. In 1995, the German Navy conducted a memorial ceremony acknowledging the crew's service and sacrifice. Their wreck site was located by Norwegian researchers in 2003, confirming its position at 180 meters depth off Fedje Island. The Mercury cargo remains aboard the wreck, raising environmental concerns. Norwegian authorities monitor the site regularly for toxic contamination. The steel flasks have corroded over 80 years, releasing mercury into the marine environment. Cleanup efforts face technical challenges. Recovering 67 tons of toxic material from 180 meters depth in active shipping lanes exceeds current engineering capabilities. The engagement taught lessons that persist into modern naval warfare. Acoustic stealth became paramount. Submarines invested heavily in noise reduction technology to avoid detection by enemy hydrophones. Maneuvering doctrine evolved to prevent pattern prediction. Modern submarines employ random course changes that defeat bearing tracking. Countermeasures developed to deceive acoustic sensors, noisemakers, decoys, and active jamming systems. But the fundamental truth remained unchanged. In submarine warfare, the vessel that detects first and attacks first usually wins. Launders understood that principle in 1945. Modern submarine commanders employ the same logic with far more sophisticated tools. The technology advanced dramatically. The tactical imperative stayed constant. HMS Venturer survived the war and continued operations until 1949. The Royal Navy decommissioned her as surplus after determining that her wartime design couldn't be economically upgraded for Cold War requirements. She was scrapped in 1950, her hull cut apart, and melted down for steel production. Nothing physical remains of the submarine that made history. What endures is the innovation, the proof that human skill combined with emerging technology could achieve previously impossible results. Launders and his crew demonstrated that warfare constantly evolves, that yesterday's impossibilities become today's tactical standards, that one crew's courage and competence can change how nations fight. That cold February morning off Norway's coast, blind calculation defeated blind chance.